Good morning in the Netherlands and good afternoon for people elsewhere in the world. I'm very happy to welcome you all today at this webinar on how to optimize the power supply for your electrolysis facility for the electrical grid of tomorrow. In this webinar, we will share our experiences in having done multiple years and various projects in this area, which have learned us a lot. And it means that we don't just have to optimize on OPEX, CAPEX, and footprint, for instance, but we certainly have to pay a lot of attention to grid requirements as well. So there is a lot going on in this area. So this will be a major attention point within this webinar, and we will show you our experience in the trends in this area. So, my name is Bart de Vries. I'm within Vonk, the commercial lead for most of our hydrogen activities, and I'm very pleased to host you with this webinar. Maybe have a quick look at the agenda for today. So first we will have a short introduction of where we are with Vonk in this industry and in general. And then obviously we'll move into the topic of powering green hydrogen facilities. So we will focus on why the power supplies are such a key element. And we'll try to give you some background information and background reasoning on for you to get a better understanding of why the things that we see in this business are having such an impact on the power supply choices and how this impacts your project as a whole. Therefore, we will focus on the developments and grid requirements to explain this in more detail. The next step is then obviously how to optimize this electrolyzer power supply given the grid requirements. We will explain what choices you can make, and we explain a number of scenarios on how these translate into practical situations for a number of fictional projects. Then we have a very nice and interesting announcement to make, so I'll urge you to stick around and don't miss it. And then we'll have a recap at the end and the opportunity to answer some questions that you might have. You can ask the questions through the chat screen within the window on the right. So, to put a bit of background on where we are with Vonk. Vonk exists for 87 years already. So we are having a lot of heritage in various demanding industry, for instance, in oil and gas. And nowadays, we are very strongly focused on making electrical solutions for the energy transition. And that's not just in the area of green hydrogen that we are focusing on today, but it's also in uranium enrichment, where we are by far and away the biggest supplier of power conversion equipment in the world. And but for instance, also in the oil and gas industry, where we are providing a lot of decarbonization solutions for their production processes. To give some examples of where we are working on, I've got a couple of slides next to this one. With Vonk, we operate on a global scale. So I'm today located in the Netherlands, but we have our manufacturing facilities in Bulgaria and Turkey and local support offices throughout the world to provide services to our local customers. As I mentioned, we are by far and away the biggest supplier of power conversion equipment for uranium enrichment. And there is a lot of similarity if you look to this industry to the hydrogen business as we see it today. So I think one of the things that we did well in this business and how we obtained this position is that we made something that's very suitable for the functionality of this particular application and then managed to industrialize and standardize this to the extent that we are the best, not only the best fitting from a technical point of view, but also meeting other demands with regards to maintenance, obsolescence management, and obviously having the lowest cost. When it comes to green hydrogen, I mentioned we've done a number of projects. So this is a project that's been open. I mean, a lot of projects are under NDA, so I can't tell too much about it, as we are well aware of in this industry. But this is a project that's out in the open, and this is a project that we have done with Sunfire. It's been delivered to Finland, to the Harjavalta site, and it's their biggest project delivered today. Another example is one that I can't be in detail on. It's the biggest project of one of the leading OEMs in Europe so far. And this one is coincidentally also the biggest project realized in Belgium. So we actually know what we're talking about. And if you may question, what is the thing that we deliver? Well, this is the current product as we have it. It's our Neya rectifier. We call it Neya as our brand. It's made by Fonk, and it's the power supply of choice for large-scale electrolysis. So where are we standing? So we would like to take an approach on the value chain and the of green hydrogen to see, to provide a bit of context on the challenges that we are trying to solve. So if you look at our Neya power supplies, we are connected on one side to the electricity grid, and on the other side, we have the electrolyser, which means that basically we are an interface within the dynamic balance of the electricity grid and the electrolyser. And if we look at this electricity grid, there is a lot going on. We see the electricity grid as a means to transport electricity from the location of its generation of electricity to the location of consumption. And therefore, there are three variables involved. There is the generation of electricity, both with its profiles and its location. The same with the consumption of electricity. And then obviously there is the grid itself, which functions as a transportation device. And there is a lot happening. If you just look at this map, we've indicated the amount of distributors of electricity in Europe, and there's a lot of them. And the bigger projects are often connected directly to the transmission operators, and there's still a lot of them as well, even having multiple per country. And these are having various issues, but not all of them have the same issues. And that's the thing that we will focus on in the next couple of slides, to get a better understanding of the challenges they face and what it means for us. So if we look at the generation of electricity, there are a number of variances that we need to consider. And it's obviously, if you look at green hydrogen, you need renewable electricity. So really dependent on the availability of this kind of electricity. And it's quite varying for different days, different times, and different seasons. To illustrate this, I've got an example of 3 different dates within the Netherlands in this case. The top one is a sunny summer day with a lot of solar energy available. The second one is actually a sunny autumn day with a lot less solar energy available, but still quite a lot. And then there's a winter day with almost no solar energy available, so hence no big peak in the middle of the day, but a lot of wind energy available. As you can see by this graphic, there's a lot of variance, not just in the power levels, but also in the daily patterns. And as you can imagine, wind on sea, for instance, has a number of very specific connection points to the electricity grid, whereas solar energy is far more spread out throughout the geographical spread of the country. If we then look at the consumption of electricity, we can see actually recurring patterns for different dates. So you see that during the day, there is a lot more consumption than during the night. But even though it seems like a recurring pattern, there is still a lot of difference. There is a big difference between working days and non-working days. There is a difference between day and night, obviously. And if you look at the distribution geographically again, you see a lot of difference between the industrial hotspots and more living areas, like, for instance, in terms of electricity use. So again, a lot of variation there. And then we have the electricity grid. That means that is a link between the two of them. I see we actually have a typo there. The top one obviously should be 2035. But these are all headlines of grid operators needing to invest a lot in their facilities. And this is caused by basically two main challenges that they face. So it's grid congestion, meaning there is too much request for electricity at certain locations to be handled by the grid. Then there's the bottleneck of having too much generation at a certain location to be handled by the electricity grid. And then they have the challenge of getting all this electricity through the grid at the same time, or from a certain location to another location. And the measures to solve this are not only very expensive, as you can see by these indications, but also take a lot of time to execute. So they are really in a tight spot. And this means that the grid operators need to take measures. And there are a lot of measures foreseen. So I've indicated the measures that have a direct input on the electrolyzer in bold. You might think that the grid balancing that I indicated in italic might be of impact as well, but that's more of a generic one, having impact on the use of the electrolyzer, whereas the impact on the power supply itself is quite limited because all power supplies can handle this. In the next couple of slides, I will deepen the tightening of the power quality requirements, because that's where the main differentiator lies when it comes to selection of the right type of power supply. One of the major importance items is power factor. So in an ideal situation, you only have the power coming to your electrolyzer that you want to use. But in practice, shifting devices cause reactive power as well. And this reactive power is drawn from the grid, causing an additional load. And as you can imagine, if the grid is already overloaded, so to speak, drawing any additional load from this grid for which you didn't sign up for is another big burden, and grid operators want to limit this. And this graphic is inserted to illustrate what the impact is of having a bad power factor. In the past, let's say 10 to 20 years ago, it was quite acceptable to have a power factor level requirement of 0.9. If you look at the additional load which this gives to the ideal situation of a power factor of 1, it's 11% more load. So that's significant. That's what we see now is basically the minimum is 0.95. And in a lot of projects, this is already being tightened to, for instance, 0.98 or even 1. And the problem with power factor is that it's cumulative. So if you already have a lot of bad equipment on a certain grid, anything that you will add to it is making it worse. So this really explains why grid operators want to tighten the requirements in this respect. Another important aspect is that of harmonics. If you look at a perfect sine wave as illustrated in the graphic above, you don't cause any distortion towards the electricity grid. However, in practice, there's no such a thing because all grids have some distortion. And this is again caused by the switching of power electronics, and it's the thing of the practice. So what we see here is that this is more or less a weighted average. So if you have a big consumer added to an electricity grid, and this is having a very good performance on power on harmonics, this is actually not that bad. If you have a very big one connected that's having a bad behavior when it comes to harmonics, it's really having a detrimental effect. So therefore, this slide example to explain this in a bit more detail. So if you, for instance, have a grid that already has 1 gigawatt of existing loads and say 3% of harmonics, if you have a 100 megawatt addition and worse harmonics, let's say 5%, its influence is relatively minor. if you would have a 1 gigawatt addition to the same grid at 5%, is really worsening the grid average. But then again, if you are adding a gigawatt plant with a 1% harmonics level, you're improving the grid average. So the harmonics requirements, if you tighten them, you can actually improve the characteristics of the grid with adding a big project. So again, this makes total sense from the grid operator point of view, that they are tightening the requirements in. And this means that we see a lot of difference from the grid operators and their requirements, depending on the location of specific electrolyzer projects and the troubles that they are facing, of course. And that translates into how you should select the right type of electrolyzer power supply. We certainly see that there is no one-size-fits-all, as we call it. So given the electrical differences for the various electrolyzer manufacturers and all the grid operator requirements differences, you need to have one that fits on both sides. And preferably avoid the use of external or additional equipment to have the optimized cost level. And in this case, I would definitely urge you to think about this and realize what the consequences could be of just selecting a certain type because that's the thing that you always do. I mean, imagine you are an asset owner, a project developer, or an EPC, and an electrolyzer OEM is coming to you and providing the electrolyzer power supply as well. And they say, this is the one that we always have, so you need to use this one. If you are not considering that this might not be the best one, you are leaving money on the table. You have added project costs, and that's not helping your business case. Vice versa, if you are an electrolyzer OEM and you are offering the type of power supply that you always offer, because you always offer it, you might have a too expensive bid to your customer. So this is something to really pay attention to when it comes to selecting the power supply for your projects. And therefore, we consider that as no one size fits all. We have a number of base topologies available in our products that are best fitting for certain types of situations, each with their own strengths and weaknesses, make them useful for certain project environments. And now I want to deep dive in a number of scenarios which emphasize the differences amongst these solutions. So the first scenario is a typical alkaline project in a country where the requirements are not too tight yet. And this is something that we typically see for instance, projects in France or in Spain. So given the not too high requirements and the relatively low voltage in comparison, relatively high current, a full IGBT solution is not the most suitable one. If you look at the harmonics requirement, you can achieve them both with diode chopper setups as well as thyristor setups. And then you see that intrinsically, looking just at the rectifier, a thyristor is cheaper. But if you include the power factor compensation cost that you need to achieve the power factor requirement, then the diode chopper actually is the more competitive one for this particular scenario. If we would have the same type of scenario, the same type of location, but then with an electrolyzer with a very high current level, and let's face it, there is only one manufacturer in this business who's quite successful, and we all know who it is, who is having this type of current levels, then basically the same kind of reasoning applies all the way up to the comparison between the diode chopper and the thyristor setup, whereas the very high current level really suits the thyristor converter, so the initial price gap is a lot bigger. And this means that the power factor compensation costs are not bridging this gap in price, and therefore the thyristor solution is the most competitive for this particular scenario. Then moving all the way to the other end of the spectrum. Let's consider a typical PEM electrolyzer with a bit higher voltage level and therefore lower current level, and facing strict requirements from grid requirements. So this is a situation that we very often see in projects in, for instance, Denmark, the Netherlands, Germany, Belgium, where there is a lot of grid congestion in place. In this case, we see the very strict requirements having a big impact when it comes to both harmonics and power factor. So even though with diode chopper harmonics levels of below 1% we have achieved in projects, this really suits for a full IGBT solution. And then the question is, which type of full IGBT solution would you need? So is it the one with just one big boost converter or the one with the chopper behind it? Well, the one with the chopper behind is more suited for the lower voltage levels and in comparison the higher current levels. And this is not applicable here. So therefore we have the booster converter only as the commercially most attractive solution. As you can see, there's quite a difference in the way we can approach the different scenarios and the type of solution that comes as the most suitable one out of the comparison and the scenario evaluation. And there's more to it. So if you look at the future, we see already that grid operators are asking more and more when it comes to, well, grid balancing, which partly is covered by the behavior of the electrolyzer, but also we see questions coming up with fault drive-through requirements and capabilities, which can be solved by the power supplies. In addition, we spend a lot of time looking at direct connections between renewables and electrolyzers, and exploring and having deep research on alternative topologies and even DC-DC connections to accomplish this. In practice, we don't see them happening a lot. We are far advanced and we execute projects as a pilot on multi-megawatt scale, but it's not really suitable for commercial use at the moment. So it's something that's coming up. And one thing that I would like to show you today, and this is leading towards an announcement, what we have is our current rectifiers are already successful. We are involved in many projects and we are very proud of what we achieved with that. But we're not satisfied yet. We realize that if we really want to make a difference, we have to get even further with our solutions. We need to have improvements on the footprint. We need to have better packaging. We need to optimize the use of materials, and we need to make it more scalable in manufacturing. So having our competitive solutions is not good enough. We want to be even better, and therefore I can announce you that we are in an advanced stage of the next generation of our Neya rectifiers. And these will really make a big difference in the industry. Depending on the specific type of topology, you will have at least 30% reduced footprint, or even a lot more. And we have very much focused on the integrated packaging. So it's designed to cover multiple cooling configurations. So if you have direct input from a dedicated cooling source within the plant, we can suit it. If you have a water-to-water heat exchanger to link to a plant cooling system, we can suit it. And if you have outdoor placement and you want to have individual water-to-air units, we can suit it as well. And we've set it up in panels, so we can make it fit for not only indoor use, but also moderately outdoor use, as we call it, and harsh environmental conditions as well. And obviously, we put a lot of effort in to have less copper involved and increase the scalability of manufacturing. And maybe to finalize for now, just a recap. I know the announcement has been very interesting, and I'm sure there will be a lot of questions on this as well, so we do this afterwards. But first, let's recap on where we are now and what we just discussed. So considering that the power supply is really an interface between the electrolyzer with the specific characteristics and the dynamic environment that we see in the electricity grid, we really need to select the right type of topology to optimize the cost of your project. And that's just more than selecting the standard one that you always have. So be compliant to the grid requirements, make it fitting to the electrolyzer characteristics, and then you have really the optimized cost levels for your projects. And to be ensured that you will make the right choices or ask the right questions for that sake. Make sure that you have experts involved early to be able to handle this in the right way. I really like to thank you for your attention so far, and I'm very, very curious to see the kind of questions that have come up during this webinar. I see a question from Bart van der Bos. Yes, it will be available for later review indeed. So Dave is already handling some questions. Dave is sitting in the room next to me, so he's helping a lot already. I see a private question on which OEMs are our customers. Well, I can't. Unfortunately, I can't address too much on the specific customers, as a lot is under NDA. So I mentioned the specific Sunfire project that we've done because that's out in the open, but we are involved with a number of the bigger and well-known OEMs. I mean, we are looking at the bigger projects, so there is only a couple of OEMs that can handle them, and we are involved with them. I see a question on the countries that we are focusing on and the capacity of the power suppliers. Well, we're mainly focused on Europe for the moment. So, and expanding this to the Middle East, because that's our initial markets where we see the most connection. And the capacity of these electrolyzers, we focus on building blocks 5 megawatts and upwards. These are standardized with some room to play with. You can basically compare it to circuit breakers where you have a certain range of application within certain confinements. So 5 megawatts and upwards. Then I see a question on the cost impact. Right. If you want to have a real indication of cost impact, I'd like to have a more personal discussion because it obviously depends on the scale, etc., etc. But what I can tell you, I mean, we are using less materials. We have a smaller footprint. We have increased manufacturing speed. So price are going down. That's for sure. So, and I even dare to say that we are the most cost-effective supplier of power supplies in this industry. Also against the smallest footprint. A question from Faisal. Yes, we will send this. We will share a link on this presentation so you can review it online. Question from Søren. Do we have electrical info? I think we can have a separate discussion on how this suits your electrolyzers. Then a question from Guillermo on the minimum power factor of different rectifier technologies for electrolyzers. Looking at partial load and in behavior in terms of reactive consumption. Yeah, so it really differs. It differs obviously per rectifier type. So the full IGBT types are having a power factor of less than of almost 1, I would say. So above 0.99. Intrinsically, a diode IGBT rectifiers are above 0.95, and intrinsically thyristors are at approximately 0.85. So you really need power factor compensation to get them up to the point where you want them to be. Then a question on how can a project developer bring you into the picture if the electrolyzer OEM is already having their own power supply? Yeah, that's a very good question, and this really emphasizes on where this market is today. I mean, we have a lot of heritage in oil and gas, so there the structures are quite well defined on who is buying from who based upon based upon a selection of equipment and so on. Whereas in this market, these scope boundaries are not that well defined yet. So if you want to involve us in projects, well, obviously you can ask them to go in contact with us. That's one route, and obviously we will do our work on our end as well, trying to get involved with them if they are not having us already. So it's a mutual effort, I would say. A good question from Tomer on a direct connection to a solar field commercially in megawatt scale. Well, this is a challenging one. I mentioned the developments that we're doing on the direct connections, as well as with specific new technology development in this respect. And it's not there yet. So let's be clear on that. So in practice, we see most often that and it's not only to do with the power supply itself, but also with the electrolyzer behavior and the rapid changes in electricity that's coming out of a solar field. So it's not an easy one to answer because there are a lot more variations to it. But if you solely look at what we are today, I think it's still, I think, a couple of years before the current type of setups with going from DC to AC and then having some kind of grid connection and then AC to DC again is being overruled. A question from Piotr. The trade-offs for the improved Neya 2.0. I think bottom line, the very big trade-off when it comes to our customers is obviously lower cost, more standardization, and a smaller footprint. These are the big draws. And oh, sorry, I misread it. It's a trade-off. So no, there is no trade-off. Functionality-wise, it will do all the same things as we already had within the existing product, and the existing product is already functioning as it should, and it is commercially successful. So because and therefore it suits what the market needs. And this one is just an improved version with more improved packaging, leading to lower cost and smaller footprint. Am I missing any further questions?
This one.
A current source PWM rectifier. We don't see this as a viable option at the moment. No. So it's really the type of approach that we are looking at now, the most suitable within environments as they are now. Do we also provide electrical models for the rectifier? It's an interesting question, Olivier. We have models, but they are specific to the customers and the project that we need them to. So maybe we can have a separate side discussion to discuss this. Then a question on the maximum size of the project that we can handle at the moment. We can handle several hundreds of megawatts with ease within a single project. I think we've covered most of the questions. Are there any further questions that I might not have addressed? A question from Martin on how many kiloamps can you supply? Yeah, there is. I mean, if you look at capacity, we can build a gigawatt per year. So that's the big question on how much power. If the question is focused on how many kiloamps within a power supply, then I really get back to the scenarios on the optimized type for a certain topology when it comes to cost. So if you're really going to in the high level of kiloamps, you're moving towards the thyristor type of setups. And with thyristor I would say it's almost unlimited. We've done projects that are in different industries that are way above anything that any electrolyzer manufacturer is using today. Yes, then there is, I missed a question on the expected lead time. We expect about 40 weeks for the new model as a lead time. Yeah, then the question, Faisal, the question on the current source PWM. Yeah, we don't see this at the moment as a viable alternative in this market. We might have a separate technical discussion on pros and cons in a one-on-one. I think we're done with the questions, so that leaves me for now with having to thank you all for your attendance and your. I see a final question from Lucy. Are we starting offering the Neya 2.0? Yes. So it's actually already going to be implemented in ongoing projects. So yes, we started offering already. Yes, indeed. Yeah, it's really it's the way forward. So it's going to make a big difference, and we want to apply it and make our customers happy with this as well. So if there are no further questions, then again, I'd like to thank you all for your attendance. If any questions might come up afterwards, feel free to reach out via email or any case or any way, any other means of communication. Again, thank you all for your attendance. I wish you all a good day and see you hopefully soon. Thank you and bye-bye.